Okay, we're continuing with chapter 3 in the geometry textbook. In this video, we're going to go through the second section, which is on corresponding parts of congruent triangles. So in the previous section, we talked pretty thoroughly about corresponding parts of congruent triangles. Not just congruent triangles, but any congruent figures. And the whole idea was that if you've got two figures that are congruent, then you have the exact same figure, but those two figures are just oriented differently relative to one another in 3D space. That's the idea. And so, but the idea of corresponding parts was that, so they're oriented completely differently, but since they're congruent, you could reorient one or both all the way to the point where they would line up perfectly on top of one another. And so whenever you line them up perfectly on top of one another, the features that overlap, the angles and the sides, those are the corresponding features. And then if you identify the corresponding features and then you put them back into into the initial position where they're oriented differently from one another, you can still match up and see, okay, which feature corresponds to which. And it makes sense that if you've got congruent figures, then corresponding features are going to be congruent as well. The corresponding angles are going to be congruent. The corresponding sides are going to be congruent because it's the same figure. Okay, and so with that then, what are we going to be talking about here in section 2? Well, in my opinion, section 2 is really more for math majors in the sense that, so yes, we talked a lot about corresponding features of congruent figures and congruent triangles in the previous section, and then in all of the example problems we worked, we pointed out all the different corresponding features in the triangles we worked with. Okay, but we never officially talked about how if we were going to try and prove that some features for a pair of triangles were congruent, outside of the features that we used to show congruence of the triangles, like the side angle side or angle side angle, we never talked about how we would officially prove that. At least in terms of if we were writing out an official proof table, what would be the reason we would give for these congruences? And so that's mainly what this section is about. So let's read through these initial few paragraphs and you'll see exactly what I mean. It says, recall that the definition of congruent triangles states that all 6 parts, 3 sides and 3 angles of one triangle are congruent respectively to the 6 corresponding parts of the second triangle. Yeah, we already talked about this, right? If we have proved that, for example, that triangle ABC is congruent to triangle DEF, these two triangles shown here, by side angle side. Okay, so yeah, this is the kind of problems we worked in the previous section example problem video. We had 2 triangles like this, and we could show that 2 of the sides were the same measure. They were congruent. 2 of the sides, and 1 of the angles were the same measure, and that angle was included between the 2 sides. Then with that, we could state that the 2 triangles were congruent by side angle side. And then based on the definition of congruence, we knew that all of the other corresponding features then of these 2 triangles must be congruent. They're the same triangle. And for most of the problems that we worked, we went ahead and showed those congruences. So, okay, we've got the side opposite this angle here in both triangles. Those are corresponding sides. So those are congruent because the triangles are congruent. Okay, now we've got the angle between this 3 tick mark side and 1 tick mark side. Those are corresponding. So those angles are congruent. And now we're just left with 1 angle. And there we go, right? We did this for pretty much every problem that we worked in the previous section. However, making these statements here about the congruence of these corresponding features, in the previous section, everything we did was technically informal from a math standpoint. That's it. That's what we're talking about here in this section. In this section, what we're talking about is if we were asked, so we started off with, we were either given or could conclude based on some information that these 2 sides were congruent, these 2 sides are congruent, and these 2 angles were congruent. And then based on the postulates we had for congruence, we were able to state that the two triangles are congruent. But if we were asked, okay, show that angle C is congruent to angle F, or side AC is congruent to side FD, or angle A is congruent to angle D, we wouldn't have had the official mathematical reasoning to write out that proof. That's it, at least in the previous section. But they're going to tell us here how you would, in an official proof, state this officially. So it says, since we can show by side angle side that these two triangles are congruent, then we can draw further conclusions, such as angle C is congruent to angle F, and side AC is congruent to side DF. The following reason, this CPCTC, which is its corresponding parts of congruent triangles are congruent, which you could come up with a statement like this for the congruence of any figures. Corresponding parts of any figure, any two figures are congruent, or any number of figures that are all congruent. Corresponding parts are congruent. Okay, but we're focusing on triangles, so corresponding parts of congruent triangles are congruent is often cited for drawing such conclusions and is based on the definition of congruent triangles. Exactly. So if we come here, there's this CPCTC, corresponding parts of congruent triangles are congruent. So yeah, if we come to this example here, it says, given that WZ bisects angle TWV, okay, so WZ bisects angle TWV. Okay, so what they're saying there is that these two angles are congruent. Okay, WT is congruent to WV, so these two side lengths are congruent. Okay, so with that, prove that segment TZ is congruent to segment VZ. Okay, so this is very similar to problems we worked in the previous section. But in the previous section, we were given something like that. We were given this setup here with these congruences, but then the prove was that it was proved that triangle WZT is congruent to triangle WZV, and we proved that because we've got this common side here. So WZ is congruent to itself, and so by side angle side, you've got triangle WZT is congruent to triangle WZV. And then from there, we would just start stating the other congruences. Because if the triangles are congruent, we know that the corresponding parts are congruent, right? Okay, so informally, we could easily state that, okay, so prove that TZ is congruent to VZ. Well, okay, those are corresponding parts. That's the last remaining leg, so those have to be congruent. Okay, so now the angle between the 2 dash and the 3 dash, those are going to have to be congruent. And then that leaves these two angles, right? Okay, so informally, this proof is easy. We just did it. But formally, what you would have to do is you would say, okay, you prove that the two triangles are congruent with side angle side. Then to state that some corresponding parts outside of the parts you used for the congruence theorem are congruent, you'd have to state this CPCTC. That's what we didn't have in the previous section. We didn't have this CPCTC argument. So that's it. That's it. That's what we're mainly talking about in this section. So now, but you could use this CPCTC to state that any of the corresponding parts are congruent, right? Now, but next what they talk about is that we can take this a step further and show other relations between features that are a consequence of this CPCTC. So again, this is really, in my opinion, this is really mathy type stuff. This is just it's just how we're making statements formally. So what they're talking about here is, let's say we wanted to state that, so that WZ bisects TV. So if we come here, WZ bisects TV. Well, okay, what they're talking about is if we show that these two triangles are congruent, right, WZT and WZV. Well, okay, then we know that we just saw that these two sides are corresponding. So this side is congruent to this side. So there you go. WZ bisects TV. But all they're talking about here is it's the official mathematical way you would state this. You'd have to first state that the triangles are congruent, then use the CPC-TC argument to state that these two are congruent. Then you could state that the bisection. But informally, we already knew how to do all of this. Informally, in the previous section, in the previous example problems, we could have stated this easily. Once we learned how the congruence postulates, okay, once we learned how to use the congruence postulates, so WZ bisects TWV, okay, WT is congruent to WV, okay, these are the same side angle side, the two triangles are congruent. Well, we know what congruence means. We just match up all the corresponding features of the two triangles and set them, and they're the same. So, okay, these two sides are congruent. Well, look, WZ bisects WV. We know what bisects means. This line segment here goes through the midpoint of TV. So WZ bisects TV. Informally, that's it. Okay, so here they give a breakdown of a strategy for proof. We're not going to go through all this. We're going to do these proofs informally. So, okay, let's look at an example. Given that ZW is congruent to YX, ZW is congruent to YX, they have that marked. ZY is congruent to WX, okay, they've got that marked as well. Prove that ZY is parallel to WX. ZY is parallel to WX. Okay, so we know that to prove that two lines are parallel, then we need to get information about if we can get a transversal between those two lines and analyze the interior angles, the exterior angles, all the different angles, then we can make a statement about whether those lines are parallel. So what we can do is, if we're trying to get information about, so we're trying to analyze whether or not ZY is parallel to WX. And we've got this transversal here. We've actually got three potential transversals, okay? So it would be nice if we could get information about these different angles, right? Here's alternate interior angles. We've got these angles between these parallel lines and transversals. So we need to know, okay, are these angles equal? Are they not equal? Or are they congruent, not congruent? So what we can do is we could take advantage of the fact that, well, we've got these two triangles here. And now we know how to analyze like relationships between triangles. Maybe they're congruent. Okay, so let's take a look at that then. So, okay, we've got two sides are congruent. Okay, do we have some other information? Well, they share a side. So triangle ZWX and triangle, let's see, it would be XYZ. They share this side here. So now we have side, congruent. So we can state that triangle ZWX is congruent to triangles. So let me get this right here. You go through the first dash side, then the second dash side, then the horizontal. So here's the first dash side, the second dash side, then the horizontal. So to triangle XYZ. And we can state this by side. So with that, now we could take advantage of the fact that the corresponding parts of these two triangles are going to be congruent. But officially, we'd have to state that. So like, okay, the angle, let's see, Z corresponds to X. So angle 1 is congruent to angle 2. But we can state that informally. However, if we were giving a proof, we'd have to state the CPC-TC. But we're stating it informally. So angle 1 is congruent to angle 2. Then we've got W and Y are congruent. And then we've got these two are congruent. Okay, so now if we come back to analyzing ZY and WX, we have this transversal here. Okay, alternate interior angles are congruent on this transversal. And if you remember from chapter 2, if you could show that alternate interior angles between two lines are congruent, then that's one of the ways you could state officially that those two lines are parallel. You don't have to show more than that. We talked about this in chapter 2. It's not like we have to show that alternate interior angles are congruent as well as some other criteria, like show that corresponding angles on the same side of the transversal are congruent as, or they're supplementary as well. No. You could show that corresponding angles on the same side of the transversal are supplementary. Then with that, you could prove that lines are parallel, or you could show that alternate interior angles are congruent. That would prove parallel. You could use any one of those criteria on its own to prove that two lines are parallel. So we've got alternate interior angles congruent here. So that's it. ZY is parallel to WX. Okay. So now next, they talk about, they give some suggestions for proving triangles congruent. So yeah, we can go ahead and read through this. We in the previous section, we worked a bunch of examples on proving that triangles were congruent. And we're going to do even more examples in this section. But here we can take a look at this as well to get some advice on how to approach proving triangles are congruent. So maybe we can get some useful tips out of this that we weren't able to use in the previous section, example problems. So suggestions for a proof that involves congruent triangles. So mark the figures systematically using a square in the opening of each right angle. We did that. The same number of dashes on congruent sides. We did that. The same number of arcs inside congruent angles. We did that. Trace the triangles to be proved congruent in different colors. That's a good idea. We didn't do that. So what they're saying is, just to make it clear, like in this example, to make it clear which triangles you're trying to analyze, you could trace the triangles in different colors to make it clear which is which. So you can kind of see both blue and red here, and then you can distinctly see the blue and the red triangle. Okay, now if the triangles overlap, draw them separately. We did do that. Yeah, that's really helpful. If you got overlapping triangles, you can just draw them separately. All right, right triangles. In a right triangle, the side opposite the right angle is the hypotenuse of that triangle, and the sides adjacent to the right angle are the legs of the right triangle. These parts of a right triangle are illustrated in the figure. So yeah, some official notation for right triangles is you call the side opposite the right angle of a right triangle the hypotenuse, and then the two sides adjacent to the right angle are the legs. Remember, you can't, with a right triangle, the other angles other than the 90-degree angle are going to be acute. They have to be. So you're going to have this one right angle and these two acute angles. And the side opposite the right angle is the hypotenuse, and then the two sides adjacent to the right angle are the legs. All right. Another method for proving triangles congruent is the HL method, which applies exclusively to right triangles. In HL, H refers to hypotenuse and L refers to leg. The proof of this method will be delayed until section 5.4. So yeah, we saw in some of the example problems we worked in the previous section that if you could prove that the two legs of a right triangle were congruent to the two legs of another right triangle, then that proved that the two triangles were congruent because of you had side angle side. Since it's a right triangle, then you know the 90-degree angles are congruent, right? If you're comparing two right triangles. And so if you know the two legs are congruent, then you have that side angle side congruence. Now they're saying another method you can use is the HL method, which if you can show that if you have two right triangles that the hypotenuses are congruent and one of the legs are congruent, then that's going to be a congruence criteria for right triangles. And that's a little different from just a general triangle, because there we've got its side angle. Side angle, which if you remember, in general, for any just general triangles, you couldn't use this as a congruence criteria. But they're saying for the case of a right triangle, you can. And the exact reason why, the proof of why you can do this, we're going to talk about later. So here's the theorem. If the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and a leg of a second right triangle, then the triangles are congruent by this HL. And this is a theorem. You can prove this. Similar to how we proved the angle side criteria, congruence criteria. Okay, so in this example here, that they do a construction that helps to intuitively illustrate this theorem. It's not an official proof, but this just gives you some intuition. So if you have segment AB and CA are given, so their lengths are fixed, and it says, note that AB is, the length of AB is greater than that of CA. It says construct the right triangle with hypotenuse of length equal to AB and one of the legs equal to CA. So it should be the case that based on this theorem here, the HL theorem, that since these are fixed, these lengths are fixed, we can only construct one triangle with these two legs. Like we have the option, the third leg can be whatever length we want. Or the second leg, the third side length, which is the second leg, can be whatever length we want. But if we're restricted to these two side lengths with this hypotenuse length and this leg length, and we know we have to make a right triangle, it's based on this theorem here. We can only construct one triangle. Even if we can pick the other leg to be whatever length we want, that length is going to be fixed. The whole triangle is fixed, is what this theorem is saying. So it starts by, it says construct CQ perpendicular to EF at point C. So we learned in a previous section, in one of the previous chapters, how to do this, how to construct a line that's perpendicular to another line going through a point. So they do that. They construct CQ perpendicular to EF at point C. Okay, now it says mark off the length of segment CA on ray CQ. So you take this length of CA, if we come to the next page, and mark this length off here on CQ. Okay, so now it says, finally, with point A as center, mark off an arc with its length equal to that of AB as shown. So you get the length of AB with the compass, put the center of the compass here, and mark off that length on this line EF. And now you've got this triangle ABC with those side lengths, with the length of AB correct and the length of CA correct in this 90-degree angle. Okay, and so what we can see from this is that you get a unique right triangle doing this. I mean, it's because we fixed this angle here. So if you think about it, they started by drawing these two lines perpendicular, okay? Then they marked off the given length here for side length CA. And then from that, we were restricted to this hypotenuse length, but we were also restricted to where the hypotenuse length had to go through this horizontal line somewhere. And so with that, then, you can just see how this, once we specified that it needed to be a right triangle, we specified a leg length and the hypotenuse length, this length here was fixed. And this angle was fixed. And this angle was fixed. Right? So now that's just a postulate. I think our intuition shows us that that's true. But we're gonna prove this officially later. So, okay, if we look at this example here, it says, given that AB is perpendicular to CD, so that means that these two are perpendicular, so it's both sides are, it's a straight angle here. Both sides are going to be 90 degrees. Okay, given that also that AC is congruent to AD. Okay. Okay, with that, prove that triangle ABC is congruent to triangle ABD. And also that segment CB is congruent to segment DB. So, okay, we've got these two sides are the same side. So there you go. The HL, hypotenuse leg theorem, says that these two triangles are congruent. Great. So we've proved this. Now, that CB is congruent to DB, well, those are corresponding parts. So you would use that CPCTC. Okay, now here it says in this next example, we emphasize the expanded list of methods for proving triangles congruent. The list includes, so yeah, here's the official list, right? In the previous section, we had these 4 separate congruence criteria. Now there's the HL criteria for right triangles. But we also have the LL criteria as well, but that's an offshoot of side angle side. That's why they don't list it. So, okay, cite the reason why the triangles ABC and ECD in the figure on the left are congruent if AB is congruent to EC and AC is congruent to ED. So, yeah, there's the HL criteria. All right. Now, what if angle A is congruent to angle E and C is the midpoint of BD? So we've got, okay, so that's side angle angle or angle angle side congruence. Okay. What if BC is congruent to CD and angle 1 is congruent to angle 2? Well, that's angle side angle. Okay, now what if AB is congruent to EC and EC bisects BD? Well, that's side angle side. And that's like the leg theorem that we talked about. But it's really an offshoot of side angle side. But like the HL is not an offshoot of anything. That's why it gets its own theorem. So for this first part, we had AB is congruent to EC and AC is congruent to ED. Well, that side angle, that's not a congruence criteria. So we're going to need to actually do an official proof to show that this is a congruence criteria for right triangles. We know it's going to be true because they gave us the theorem, but we haven't proven it yet. Okay, but now if we come here, the Pythagorean theorem is going to give us a hint on how we're going to be able to prove this HL congruence criteria. So it says, the following theorem can be applied only when a triangle is a right triangle. The Pythagorean theorem is for right triangles. Proof of this theorem is delayed until an upcoming chapter. So the Pythagorean theorem, it says that the square of the length of the hypotenuse of a right triangle equals the sum of the squares of the length of the legs of the right triangle. So yeah, this is really, really useful. If you've got any general right triangle with the length of the legs given by A and B and the length of the hypotenuse given by C, for any right triangle, it has to be a right triangle. It has to be a right triangle. It's always the case that if you sum the squares of the legs, you get the square of the hypotenuse. That's it. That's the Pythagorean theorem. And we're gonna prove this later. All right. Now, they also give this square root property, which we can use this with the Pythagorean theorem if we're solving for one of the side lengths or the hypotenuse. And that if you've got a variable squared on one side of an equation is equal to some constant on the other side, then it says that x is equal to the principal square root of that number. That's what they're saying here. And this is basic algebra. And technically, if you know the square root property, then the technical answer to this is you put a plus or minus in front, because there's two numbers. Like if you had x squared is equal to 4. Well, if you're solving this like in algebra, the question is what number, when you square it, do you get 4? Well, there's two numbers when you square it, you get 4. 2 squared is 4, and minus 2 squared is 4. Right? However, they're not, for this property they just gave us here, they're not giving us the negative. They're not telling us the negative. They're just going to say, well, this is equal to 2, because when we're dealing with triangles, like in geometry, we're not dealing with negative features, negative angles, negative side lengths. No, everything's it's these everything's positive in geometry in that sense. So, but okay. So if we look at this example here, it says find the length of the third side of the right triangle. This right triangle, given that if find C if A is equal to 6 and B is equal to 8. So if A is equal to 6 and B is equal to 8, you've got A squared plus B squared is equal to C squared. So 6 squared is 36. 8 squared is 64 is equal to C squared. 36 plus 64 is equal to 100. So we're saying what number when squared is equal to 100? Well, that's the principal square root of 100, which is 10. Now, in algebra, we would technically put this plus or minus here, and the answer would be plus or minus 10, but we don't need the minus 10. This is a positive, it's a side length, so we just put 10. We just put the positive. Okay, so we just solved for the hypotenuse. In this next example, we solve for a side length. So find B if A is equal to 7 and C is equal to 10. So A squared, 7 squared is 49, plus B squared is equal to C squared. So subtracting 49 from both sides, we get 51. So B is equal to the principal square root of 51, which if you put that into the calculator, you get, it's about 7.14.